Hello, today we're going to talk about structure 2.4.3, which is all about alloys. And alloys are mixtures of a metal with other metals or with nonmetals, and they tend to have enhanced properties over the pure elements. So as I just said, alloys tend to be mixtures of metals with another metal or with another element. We've looked at alloys in the past, most likely, where metals tend to have these positive cations surrounded by the mobile valence electrons, and that's still true for alloys. You're just going to replace one metal with maybe a different metal. And this would be called a substitutional alloy. Or sometimes you might have an element stick in the space between, and that would be called an interstitial alloy. And you can have lots of different mixtures of metals, or another common element that's mixed in is carbon. So let's go over some common alloys. You don't have to memorize these, but they are some good ones to recognize. Like brass is an alloy of copper and zinc. Bronze is copper with tin. Solder, like if you're soldering something together, is usually lead with tin. And then steel is usually iron with carbon. And then stainless steel is iron with carbon and chromium. And then finally, rose gold, we have gold, of course, and there is some copper to give it that distinct color. So these are just some common ones that show up a lot. And some of the reasons why we would put these together is that the alloy might be more dense. It might be have a higher tensile strength, especially in regards to things like steel. So steel is one of those interstitial alloys where the iron ions and then the carbon atoms fit in between the irons to give it more strength, more rigidity. Another one would be like with solder. Solder has the lead with tin, and it winds up being at a lower melting point than whatever you're attaching it to. So that way, like if you're soldering on like an electronic component, you're not melting the electrical board. You are only melting the solder itself. So having a difference in melting point could make it a very beneficial alloy. It could be just cosmetic, so things like rose gold, it's just for color. Whereas stainless steel, you're going to have that bit of chromium. Not only does it give it a shiny look to it, but it also helps to prevent against rust. So all of these different alloys, they're made for a reason. They're going to have some property that the pure metal does not, which is why we make the alloy. So like I said before, alloys typically are going to be less malleable and less ductile. So it's not as easy to bend and shape or draw into wires. And that's because the different atom will disrupt the lattice structure. So if you have your metal ions, even if you just change a few of the atoms to a slightly different one, like maybe it's a little bigger or a little smaller, it's still going to disrupt that lattice structure. And so it will make it less malleable and ductile. Another example would be like aluminum alloys. I don't have a specific name for these, but if you take aluminum, which is a very soft, malleable metal, think of aluminum foil. You can bend it and shape it. If you make an alloy with something like maybe copper, that copper is going to give it a lot more strength. It's going to make it harder, make it more difficult to bend. But having the aluminum in there still keeps it low density. So that's why you get like aircraft parts that have that really low density, so they're very lightweight. But having the additional metal will give it the structural integrity that it needs. Now, there's a few ways that we can approach protecting metals against rust or corrosion. One of those is just by painting the metal. So a lot of times you'll see painted things, just not, I mean, they try to make it look good, but the main focus is to keep it from rusting. Like, you don't want your airplane to rust out from underneath you. So painting it helps protect it in that way. But there are a couple other methods, and one of those we call galvanizing. And that's usually with zinc, where you're going to either coat it in zinc or include like additional zinc atoms, especially near the surface, because zinc will corrode, oxidize at a much slower rate than many other metals. So that helps protect it over time. You could also have sacrificial metal methods. Sacrificial. And the big example that I like to use of this one is the Statue of Liberty. But that's where you would have the outermost layer of whatever you're building. The outermost layer is something that you're intending to corrode. All right. So imagine like this. If I have my copper, the top layer of copper will form copper oxide. It might be copper 1 oxide, copper 2 oxide. But once the top layer forms the oxide, it's corroded, that then serves to protect the metal underneath. So that top layer is sacrificial in that it's no longer a metallic substance per se, it's ionic, but it is protecting what's underneath it. So let's look at a couple examples from this section. When would an alloy of aluminum and nickel be preferred over pure aluminum? So it might be a situation where you need something that is less malleable. It's going to need to hold its shape better. And that's why you would use an alloy of aluminum instead of just pure aluminum. Now let's think about this question. How can you separate the elements in an alloy? Remember that alloys are mixtures. They're mixtures of metals. Most of the time we think of mixtures, we can separate them using their physical properties. It becomes a little bit more difficult when you have an alloy because metals, they're forming a pretty metallic structure, right? They're metals. Their cations are mixed together, and the delocalized electrons are through them. So there's a couple strategies if you want to purify an element. You could use melting point, but you'd have to make sure that the elements have two very different melting points, and you'd have to heat it very slowly. And even then, it's going to be a little difficult to separate. You could also, if one of the elements in the alloy is magnetic, you could melt it, use a magnet to separate out just the element that is magnetic. So it becomes a more tricky problem than traditional mixtures that we've thought of before if we're trying to separate them out. And this section links back to structure 1.1 if you've already gone over that section. Why are alloys more correctly described as mixtures rather than as compounds? And it's really because the metals in the alloy are not necessarily bound directly to one another. You might have an atom of copper, and if, let's say, we're making brass, zinc, and they can be mixed together, and the electrons are free to move throughout them. It's going to be different from, say, just a pure metal, like if I just have zinc with the electrons moving throughout them, or if I have something like zinc chloride, where I have that positive zinc ions and the negative chlorine ions, where the electrons are not free to move around. So this would be considered a compound. This would be a metallic substance, and this would be a metallic mixture with the different elements.